5,000 players, 20 updates per second each, and the server is at 40% CPU, yet new players get connection refused. The culprit? TCPs per connection overhead. Let's break down why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover TCP versus UDP. TCP and UDP are the two transport layer protocols that define how data moves between networked applications. The core mechanic: TCP guarantees ordered, error-checked delivery by establishing a persistent connection and retransmitting lost packets. UDP sends datagrams with no connection, no ordering, and no retransmission. This single difference dictates everything about their behavior under load. You've seen the handshake, you know the flags, but do you really know what's in every TCP packet? Because you'll be debugging it at 3 a.m., staring at a hex dump, and wondering why your connection dropped. Let's walk through all 10 fields. The article mentions that UDP uses one socket for all clients. Here's a concrete Java snippet showing a UDP server that handles multiple clients on a single datagram socket without per client state. The article notes UDP's checksum is optional in IP4. In practice, disabling it is dangerous because corrupted packets will be silently delivered. Always enable checksums, default in most stacks, unless you have a very specific reason and handle corruption at the application layer. The article describes TCP connection exhaustion at 5,000 players. Here's a minimal Java server that quickly exhausts the default file descriptor limit by creating many TCP connections, illustrating the resource overhead. Here's a bash script to capture a TCP SYN packet and decode the header manually. Run it with sudo and you'll see the hex dump. The offset plus flags field tells you the header length and whether SYN is set. TCP's reliability isn't magic, it's engineering. Before a single byte of your data travels anywhere, TCP performs a three-way handshake. The client sends SYN, the server replies SYN ACK, and the client confirms with ACK. Only then does data flow. This ceremony establishes sequence numbers on both sides, which is how TCP tracks every segment and detects anything that goes missing. Here's a minimal TCP Echo server. Notice that the server socket binds to a port and listens. The accept call returns a dedicated socket for each client, full duplex, stream-oriented. The underlying stream guarantees every byte arrives in order. And here's the TCP client. The socket constructor does the three-way handshake internally. If the server is unreachable, it throws connect exception. Once connected, we send a message and read the echoed response. UDP's design philosophy is the opposite of TCP's. Get the data out as fast as possible and let the application decide what to do if something goes wrong. There is no handshake, no acknowledgement, no retransmission, and no ordering guarantee. You send a datagram and it either arrives or it doesn't. Here's a UDP Echo server. Notice there is no accept, no handshake, no connection. The server just sits and waits for datagrams to land in its socket buffer. Each receive, call processes exactly one independent packet. And the UDP client. Notice that send returns immediately even if the server is down, no exception. We set a timeout on receive to handle lost replies. This is manual reliability, something TCP does for you automatically. The choice between TCP and UDP isn't about which is better, it's about which constraints match your problem. Run through this mental checklist every time you're designing a networked feature. Ask, what happens if a packet is lost? If the answer is the entire operation is corrupt, use TCP. If the answer is the app can recover, UDP is worth considering. Beyond delivery guarantees, TCP has two critical mechanisms that UDP lacks entirely: flow control and congestion control. Flow control prevents the sender from overwhelming the receiver's buffer. Congestion control prevents the sender from overwhelming the network. UDP has none of this, so a misbehaving UDP application can blast packets at line rate, causing buffer bloat. Let's look at concrete examples where the TCP UDP choice made or broke a system. Video conferencing uses UDP almost exclusively because a lost video frame is replaced by the previous frame. Online banking uses TCP because every request must be atomic and complete. IoT sensors often use UDP with application-level ACKs for critical alarms. UDP amplification and reflection DDoS is a serious threat. The attacker sends a small UDP request to an open resolver with a spoofed source IP. The resolver sends back a response that can be 50x larger. Mitigation starts with BCP38 ingress filtering at network edges. Here's a SysTool configuration to secure your TCP stack. Enable SYN cookies to prevent SYN flood attacks. Increase listen backlog, enable timestamps for sequence number randomness, and disable source routing. Rate limit ICMP to reduce UDP stream tearing risk. TCP and UDP carry plaintext by default. If you can see the packets, you can read the data. The fix is simple: TLS for TCP, DTLS for UDP. These add encryption at the transport layer, making the payload unreadable even if captured. Here's how to wrap a raw TCP socket with TLS 1.3. This is what your application should do, not send credentials in plaintext. TLS 1.3 adds about 1 round trip, but kills eavesdropping. TCP is point-to-point only. If you want to send the same data to 1,000 receivers with TCP, you open 1,000 connections and send the same bytes 1,000 times. UDP solves this with multicast and broadcast. One packet sent from the source, and the network delivers it to every interested receiver. Here's a Java receiver that joins a multicast group and prints incoming datagrams. If you're running this in production, make sure your network infrastructure supports IGMP snooping. Otherwise, every multicast packet floods all switch ports, and that kills performance. This is the same issue we highlighted at the start. Here's exactly why that happened. A game server using TCP for 60 updates per second from 1,000 players collapsed under connection state overhead. Each TCP connection consumes about 3 KB of kernel memory for the socket structure. At 5,000 concurrent players, the server must maintain 5,000 open file descriptors, but the ulimit was set to 1024. The kernel ran out of memory, and the server crashed. The fix was to switch from TCP to UDP for real-time position updates. UDP is stateless. The server reads datagrams from a single socket, and packet loss affects only that specific message. For critical events like player death, we implemented application-level ACKs with timeouts. The result: the same hardware now handles over 10,000 players without connection exhaustion. This is the code that caused the incident. The server sends position updates over TCP for each player, 60 times per second. Each TCP connection consumes kernel memory, and with 5,000 players, the ulimit and memory are exhausted. The fix was to use UDP for these updates. A common production trap: TCP throughput drops to near zero because the receiver's socket buffer is too small. The default is often 64 KB on some systems. For high-throughput streams like video uploads, increase SORCVBUF to tens of megabytes. UDP packet loss is silent send, succeeds even if the destination doesn't exist. In production, this means retry logic is your responsibility. A common failure: a monitoring agent uses UDP and misses critical alerts because no one implemented ACKs. Always implement application-level ACKs with timeouts when using UDP for essential data. Always use incoming packet get length when converting the byte array to a string, not receive buffer length. The buffer is pre-allocated at 1024 bytes, but the actual datagram might be 12 bytes. If you use the buffer length, you'll get 1012 null characters appended to every message, causing silent data corruption that's surprisingly hard to debug. Here are some debugging commands to diagnose TCP and UDP issues. Use netstat-s to check retransmission counts. Monitor socket buffer drops via /proc/net/TCP. Use TCP dump to capture packets. And simulate packet loss with Netum to test your application's behavior under adverse conditions. Let's run through some common interview questions. Explain the three-way handshake. SYN ACK, ACK establish sequence numbers. When would you choose UDP over TCP? For real-time, loss-tolerant traffic like video or games, what is head-of-line blocking? A lost TCP packet stalls all subsequent data until retransmitted. And a few frequently asked questions. Is UDP faster than TCP? Yes, due to no handshake and smaller header. Can UDP be reliable? Yes, by implementing ACKs and retransmission at the application layer. What is QUIC? A modern transport protocol over UDP with TCP-like reliability, used by HTTP3. Key takeaways: TCP guarantees delivery at the cost of latency and per connection state. UDP trades reliability for speed and scalability. Choose your protocol based on data criticality and frequency. Always encrypt with TLS or DTLS, and monitor retransmissions and buffer drops in production. Ready to go deeper? Up next, the OSI model, then HTTP 1.1 vs HTTP 2 versus HTTP 3, QUIC, then WebSockets explained. Find them all at thecodeforge.io. Thanks for watching. The full article and code examples are covered in detail at thecodeforge.io.